Okay, so the last thing that we are going to do, nope, I don't want to save that, is we are going to open up class 3. Sometimes we have issues where our slope changes for some reason or another, right? And I'll give you an example from our research. So most of the time when we're thinking about latent growth curve modeling, we're assuming that we're talking about across time in some way, right? In our research, we like to look at measurements of mood across a day with the idea that sometimes something happens throughout the day that changes mood. And so oftentimes we will have day, and at some point during the day, a person starts to drink, right? And so we might have mood measurements throughout the day, and we can plot mood leading up to a drinking event. And this is done in multi-level modeling or latent growth curve modeling in the exact same way. We're just looking at this is time 1, time 2, time 3, time 4, time 5, time 6, time 7, time 8, time 9. So let's say we have 9 time points, right? And across time, we see that negative mood is increasing like this. And then it hits this spot, and it does this. A linear slope won't capture that, right? And so we have to find ways to capture this in using a different approach. And we've got an approach that we can use in latent growth curve modeling called, oh, what the heck? Hold on a second. I'm actually writing a paper on a new way to do this. So let me just pull this up quick. Can't believe I can't remember the name of this. Driving me crazy. Now everybody on the internet gets to see what my Dropbox looks like. Piecewise. There we go. And here's actually the piecewise thing that I'm working on. It doesn't matter. So piecewise growth curve modeling. And I don't know why that seems so hard to get to because it's just 2 pieces, right? um, but this is kind of the stuff that we do right now. And actually, this is really cool because you can move your intercept around here as well. So in my research, what we do is we say that the time that a person started drinking is set as 0, right? And then we have -1, -2, -3, -4, -5, 1, 2, 3. And so that means when we do a latent growth curve model on this, what is my intercept? It's going to be actually, assuming that this is mood, right, negative mood, my intercept winds up being the negative mood at the drinking spot, right? Because I've set that as my 0 time point. And so that tells me, like, here's the average negative mood when somebody starts drinking, and this is the slope, at least for this portion, leading up to a drinking event. Now, unfortunately, if we use this type of coding for time, then this just keeps going this way, right? And it works great right up until here, and then you just have these increasingly large residuals, right? So we have to change this. We have to do something else. And what we do is we set this to go just like this, just like it does here, right? But when we hit this point, we will, instead of coding this 1, 2, 3, we will code this 0, 0, 0. It's saying, like, once this slope hits here, stop. The slope never goes on, right? And then we might do something like this, 0, 0, 0, 0, 0, 0. That keeps our intercept the same, 1, 2, 3. And that says, at this point, take over and give us a new slope. And so we will get a slope that encompasses this time point and a slope that encompasses this time point. We'll get 2 different slopes. And we can do this in latent growth curve modeling very simply. So let's have a look here. So Has everybody opened this up now? We've got time 1, 2, 3, 4, 5 in group 3, right? Let's start by just doing this, and let's go 0, 1, 2, 3, 4. This assumes just a simple linear slope across time, right? Save, run, and let's check out our model. Model fit is not very good, right? We do have a slope across time. That slope is 1.474. Let's have a look here. Let's open up our oops, I did it again. Scatter t over time. It's kind of tough to see here, but what we really have is a slope that's kind of flat here and then takes off when it gets to here. Now this looks like it could also be what? Could be two different things going on here. What's the other thing? Could just be a quadratic effect, right? Yeah, so we can test that. Now, from a theory perspective, you should know if this is quadratic or if some event has occurred that would change that slope, right? And that's the difference between a piecewise and a quadratic, is a quadratic might just be like stuff is going on, whereas a piecewise might be like something drastically different occurred. So if we test this quadratic, and I have not done this yet either, so we'll see what happens. Well, that fits a lot better than our last slope, right? We've got an RMSEA of 0.127. That's not great. Our CFI is good. TLI is good. Chi-square is still statistically significant. And when we look down here, we do see significant quadratic effect, right? And a significant slope. But in this case, oh, and maybe your model is best explained by that. But let's go, we have 54 with a degree of freedom of 6, right? Now let's change this. Instead of a quadratic slope, let's say that we know that there's an interrupt. There's a time point where things get wonky. We're going to change this to 0. We're going to change this to -1. We're going to change this to -2. And then this should be what? Based on what I wrote up here? 0. And this? 0. Okay, so now what we're doing is we're modeling two different slopes. Our intercepts should be the same, right? Like this should not change. It's going to be roughly the mean of time point 3. Yeah. All right, so let's run this. What was our degrees of freedom before? It was 6. And what was our chi-square? It's like 54, right? So our degrees of freedom are not going to change because all we're doing is changing the type of slope. We still have 3 or 2 slopes, and we still have 1 intercept, right? None of that stuff has changed. None of our model parameters have changed. Nothing has changed. So we can't compare these in the sense of like this one has a 1 degree of freedom difference or what. But you can say one fits better than the other, right? And I don't think anyone's going to argue with that. It would be difficult. It would be more difficult if they were both at a degree of freedom of 6 and a chi-square of 54. But in one case, one model clearly fit poorly. We didn't reach our kind of conventional thresholds that we'd like to see. And then in one case, the model fit quite good. And so this model actually fits fantastic, non-significant chi-square. And as we look down here, let's walk through and talk about what this means. What is our intercept at this point?
Is that 53?
Say that again?
53?
Oh yeah, it's time 3. Yep. So it's roughly the mean at time 3. Let's have a look over here. Let's go sum t if time equals 3, 2.6, and here we have 2.605. Pretty close, right? Right? It's not going to be perfect. We have a slope prior to time 3 of 1.071, leading up to time 3. And from time 3 to time 5, our slope is 1.957. It increases dramatically, right? Like our slope almost doubles in value from 1 to almost 2. Then we can look at our variance. We have a lot of variability in our intercept, right? A lot of variability in slope, and a lot of variability in our slope afterwards, our second slope, right? So that means that people's trajectory leading up to the event, whatever that event was, varies a lot, and people's trajectory after the event also varies a lot. But we have kind of average effects across people of 1.071 before the event and 1.957 after the event, right? Does that make sense? So, thinking about your own discipline, I'm just curious, what are some sort of events that might change a slope across time?
Maybe if we're looking at mood and something, maybe if someone exercises during the lunch.
Perfect, right? So yeah, I mean, it could be you're looking at mood across time, which is roughly flat, and then they have they exercise, and then you see an increase in mood, or maybe a decrease in negative mood, right? Alternatively, what you might see is a flat effect on both sides, and just a really robust change at the intercept point, right? So you could move that intercept. Maybe their positive mood just jumps up, and then it holds steady. I don't. But yeah, no, that's a good example. Business folks, what's a good example from you guys? A recession? Oh, that's interesting. I was thinking about like earnings before, earnings under the old CEO, earnings under the new CEO, right? Yeah, right. So there's all kinds of like interesting potential ideas. Clinical folks, the one that I always draw from is like, oh, you started a clinical trial, you moved into the intervention phase or something like that, right? Yeah. Yeah.
But these values, they're not indicating a chevron.
No, these aren't. You're right. I mean, these ones are indicating something closer to like this, right? Like they're going like this and then like this. Sorry, I gave you maybe a bad example to start with. I wanted to give you this example just because it made sense to me, but yeah, go ahead.
Does that mean that we can test different inflection points by just splitting slopes?
Oh yeah, you can absolutely. You can move your slope around in this way too, right? Or I mean your intercept around in this way too.
Then, yeah, so if there are two events of interest instead of one,
What would you do?
so would I kind of segment that timeline to, I don't know, so if you test one event and then test another and then test another zeros at different points?
What would you? So maybe, Aaron, do you have an idea? I have an idea. I've never had this happen, but I have an idea. Go ahead, Aaron.
Well, I was just wondering if you would like split it if it wasn't like an event, but like discretionary accruals, like there's a change afterwards for like a time period, but then it just goes back to like what the old CEO was doing. So it's just a dip in the original. So would you separate that? It's not necessarily an event. It's just that event has expired.
Yeah. So the thing that you bring up, and actually what you bring up as well, yours is actually easier, right? Because you have an event, and then maybe a quadratic effect or something that occurs post-event, right? You are talking about two different intercepts, though.
So it's like 2s1s2, and then we'll account for that area, and then again s1s2 because it changes from that point.
Yeah. So I think you have an I1 S1 and an I2 S2, in which case I'd have to think about it a little bit on how you would model, because, oh, I'm sorry, and then you would have, an I2S3. No, you wouldn't.
I1S1, I1S2, then I2S1 and I2S2. So
Yes.
there's 4.
Yeah, I think that's right. I mean, I don't know though, because you're talking about 3 slopes.
Yeah.
We have to have a third slope in there. I1S1, I1S2, I2S3 perhaps? I'm not sure how you would code that. There's got to be a way to code it. I've just never done it. That's an interesting thought though, like how you would code a second interrupt in something. I'm sure that there's a way to do it. I'd have to do a little bit of reading. But I'm sure that there's a way. And if there's not, you can invent one, and then you can be famous for it. I'm just kidding. All right. That is all that we have to cover for today. The last thing that I want to talk about is what your homework is going to be for this week. So, it is a linear growth model, a simple linear growth model, but it's 2 of them, right? And the idea is that sometimes we have 2 different processes that occur simultaneously. And in this case, you'll have time 1, time 2, time 3, and time 4 of x, and time 1, time 2, time 3, and time 4 of z, okay? We're going to have an intercept, intercept, slope, slope. And it will look like this. I'm not going to number all these, but you know that the intercepts are all numbered as 1. The slopes are all numbered as 0, 1, 2, 3, right? You will have to name these differently, just FYI. I2, or I mean, maybe I1, I2, S1, S2. These are already going to be correlated. And for your homework, what you want to know is, as this slope changes, does this slope also change? How do we do that? Say that again?
Covariance.
Yes. So you can just say S1 with S2. That will tell you if S1 changes, S2 changes. What if you think that S1 is causing S2? Yeah, then it would be on, right? Instead of a covariance, it would be this. Can you test the difference between a with and an on? Yeah. Why can't you?
It's the same thing.
It's the same degree of freedom, right? It's 1 degree of freedom. You can look and see if one model clearly fits better than the other. And there is a way to actually test this using log likelihoods that I haven't showed you guys, and I'm not going to show you guys right now anyway. But either way, for your homework, like you can look at both of these and decide which one of these clearly fits better. From a theory standpoint, right, gamma radiation should increase size and strength, not the other way around. So at least the line going up doesn't make sense, but maybe just a simple covariance is fine. Yeah.
So when you say test the 2 models, so the 2 models would be like one where it's like they're covariant, and the other one where one's causing the other.
Yeah. Yeah. So, all right. Any questions for today? No? All right, cool. Well, have a good weekend. That is it. I will get the last video uploaded right now. You guys will be ready to go. You coming to take a picture?
Yes.
Let me get my hair done.